Welcome back to this course ILP, DLP and TLP. In this lesson we start a new course on exploiting thread level parallelism, TLP, to improve the throughput of a single core. The purpose of this lesson is to motivate executing multiple threads on a single core, or core multithreading, as I like to call it. First, as usual, the motivation. Remember that I presented a slide with some ILP challenges and an outlook of the remaining modules. One of the issues on this slide was how to efficiently use ILP resources. If a program doesn't have sufficient ILP to exploit to keep all functional units busy, how can we make effective use of all ILP resources available? And the idea that I will discuss now with you is to do multithreading on a single core, which I call core multithreading. Another motivation. This shows the results shown by Dean Tilson in a very famous paper that was presented at the International Symposium on Computer Architecture in 1995. It shows the execution time breakdown of the Spec 92 benchmarks on a wide issue and 8-way superscalar processes. And we see that for most applications, vertically or the different applications, most of the issue slots are wasted. Only about 90% the CPU of the total execution time, the CPU is really usefully busy executing instructions. So we see that most issue slots are wasted, and most of the time the processor is waiting. The number one reason, which is hardly visible in the legend, but which is highlighted here, is because of data dependencies between short floating point instructions. Floating point instructions with a relatively short latency. The number one reason why the processor is stalling most of the time is data cache misses. So we see that most of the issue slots are wasted, and this motivates using multiple threads of execution and to execute them in parallel on a single execution core. Here's another motivation, right? What is the next step on ILP? How can we exploit more ILP? Can we build bigger caches? Can we make the instruction window size larger to find the ILP present in the application? Can we use more miss status holding register, or do we continue to develop better branch predictors? Of course we should, because our goal is to make the execution of a single thread as fast as possible. But there is the malicious law of diminishing returns, which tells us that to get the remaining 5% of the potential benefit requires more and more effort. Here's another motivation, the very long memory latency. Suppose we have two levels of cache, L1 and L2, and we assume that the cost of a miss penalty, the cache miss penalty, is 20 clock cycles for level 1 and 200 clock cycles for level 2 miss. And also assume that the miss frequency is every 20 clock cycles for a level 1 cache miss and every 200 clock cycles for a level 2 cache miss. Let's now try to estimate, using these assumptions, how much time it will require to execute 200 instructions on average. Of course, if we have a baseline CPI of 1, without cache misses, we would require 200 cycles. And this time diagram shows that under these assumptions, we will require 600 clock cycles. We compute for 20 cycles, then we have a level 1 cache miss which has a miss penalty of 20 clock cycles. Then we have another 20 cycles of computation, then another level 1 cache miss, And finally, we will have somewhere a level 2 cache miss requiring 200 clock cycles. Every 200 instructions, we have one level 2 cache miss and 10 level 1 cache misses. So the total time will be 600 cycles under these, of course, contrived assumptions, but this yields a slowdown by a factor of 3. So what can we do to make better use of the ILP resources that are available anyway? We should keep them busy, right? If the ILP is exhausted in a single program, we can try to exploit thread level parallelism. The basic idea is to use the abundancy of resources that we have to be able to execute many instructions, to keep many instructions in flight, to try to execute them in parallel, to execute multiple threads simultaneously or in a time-shared manner. And we would like to tolerate the long memory latency by executing a different thread each time the current thread is blocked. As shown in this time diagram, the dark purple boxes are the time the processor is computing, and the light purple boxes is the time the thread is waiting for memory. So instead of waiting for the first thread for data to be returned from memory, we instead execute a different thread, and then execute a different thread, and then yet another thread. And by the time all threads are stalled waiting for memory, we start the first thread again because its memory value has been returned from memory. This completes this lesson. Thanks for watching. In the next lesson, we will look at software multithreading, which is a very old form of multithreading, and also highlight some features of hardware multithreading. Hope to see you back.